Hello to all my dear learners. I am Aishwarya Sharma, Civil Wallah, welcoming you on the platform Gate Wallah. So today we are going to start our third session on one shot series, and we are talking about RCC. And in earlier two sessions we have completed introduction properties of concrete as well as introduction to limit state method. So today is our lecture number 3, and in this lecture we are going to study about the rectangular beam in Flexure. Means we are going to cover singly as well as doubly reinforced beam, rectangular beam in Flexure. Okay, and in next topic we will be discussing about the flanged section. Okay, so let's start the session, my dear friend. So topic name is rectangular beam in Flexure, and this is the agenda for today's session. Topic number 1 is analysis of singly reinforced beam, with which we are going to start. Afterward we are going to see analysis of doubly reinforced section, and then we are going to see the design of doubly reinforced section, and in the end we will be covering numerical. So 3 topics are there today, and 3 numericals we will be covering at today's session. Okay, so let's start here. So analysis of singly reinforced beam. My dear friend, for analysis of singly reinforced beam, we do have 4 steps. Okay, analyze means to calculate the ultimate moment of resistance. After getting the value of ultimate moment of resistance only, we will be able to calculate the maximum factored load or maximum working load. Okay, so it's very important to, if we want to analyze a beam, then we must know that how much it can bear in bending. So based on that we can calculate the maximum safe load. Okay, so there are total 4 steps for reaching moment of resistance or maximum safe load. So first is calculation of limiting depth of neutral axis, or you can say balanced depth of neutral axis. Second step is to find the actual depth of neutral axis, and in third step we are going to we are going to make a comparison between actual and limiting depth of neutral axis, and in final step we will be seeing how to calculate the moment of resistance, and that moment of resistance can be converted into the maximum safe load or minimum safe load, like that. Okay. Okay, so question number 1 is, or topic number 1 is calculation of limiting depth of neutral axis. My dear friend, limiting depth of neutral axis calculation is based on the strain. You might be remembering your assumption number 2 and assumption number 6. Assumption number 2 says at the time of collapse, the maximum compression concrete is going to have a strain of 0.35% or 0.0035. Similarly, assumption number 6 says at the time of collapse, strain at the level of CG of tensile reinforcement should not be less than 0.2% plus 0.87 Fy upon ES. So if we are going to get these strains, these corresponding strains at concrete and at steel respectively, then such a depth of neutral axis is going to call as the balanced depth, or you can say limiting depth of neutral axis. Okay, so limiting depth of neutral axis is such a depth of neutral axis when strain at the outermost concrete fiber is 0.35% and strain at the level of steel CG of steel is 0.2% plus 0.87 Fy upon ES. And if you are going to equate with the concept of similar triangle, then we can write 0.0035 upon XU is equal to 0.0020 plus 0.87 Fy upon ES divided by D minus XU. Okay, and we all know the Young's modulus for steel is 2 into 10 raised to the power 5. It is 2 into 10 raised to the power 5. So we can get the value of XU lim. So on solving this equation, you will be getting this, and from this expression again we can conclude that limiting depth of neutral axis is going to depend on grade of steel. It is going to depend on Fy, and Fy is grade of steel. Okay. its yield strength of the steel. So based on the grade of steel, you will be having the value of Fy. Are you getting it or not? And there is one more hidden thing here. Actual depth of neutral axis, limiting depth of neutral axis is depending upon the grade of steel as well as the Young's modulus of the material. Young's modulus of the material, what? Young's modulus of steel. Because here you have substituted the value of Es. Okay. So sometimes they may ask on what are the factors on which your axial limit depends. So there, if Young's modulus of material is also given, you have to select that as well. Okay. And yes, if we are considering the Young's modulus of steel constant, which is obviously yes, it is equal to 2 into 10 raised to the power 5 MPa or Newton per mm square. So after substituting that value, you are going to get axial limit this. And if you are going to substitute 250, 415 and 500, so you are going to get this standard values 0.53D, 0.48D and 0.46D. Are you getting the concept or not, my dear friend? So this is the concept of limiting depth of neutral axis. After limiting depth of neutral axis, we will be studying how to get the actual value of neutral axis. Actual depth of neutral axis. Actual depth of neutral axis is that depth where about which compressive forces and tensile forces are same. Okay, so that is why it is neutral. So again we have to calculate net compressive force. Again we have to calculate net tensile force. Okay, and in last session I have already told you the study of a stress block. So you know that this graph is parabolic. After that it is becoming rectangular, and this rectangular portion is 3/7 and this parabolic portion is 4/7. Okay, so out of total XU, 4/7 part lies in the parabolic zone and 3/7 part lies in the rectangular zone. And we have seen that the resultant compressive force due to the rectangular portion as well as due to the parabolic portion is coming out to be 0.36 FCK BXU. Out of this 0.36 FCK BXU, 0.19 FCK BXU is due to rectangular block and 0.17 FCK BXU was due to parabolic block. Okay, and what is the location? Location was it is 0.42 XU from the topmost fiber. So if you want to calculate the actual depth of neutral axis, then simply you have to equate the compressive forces with the tensile forces. And my dear friend, the compressive forces here are 0.36 FCK BXU and the tensile forces are 0.87 Fy into AST. Are you getting it or not? So by this concept you can get the value of XU. There is one more way to represent this expression, that is XU is 0.87 upon 0.36 into Fy upon FCK into AST upon B multiplied by D divided by D. So this is one more format. Okay. So I think it will come 2.24 something, 2.4 Fy upon FCK AST with the effective area of concrete into D. Are you getting it or not? Okay. Effective cross section, not effective area of concrete. BD is effective cross section. Okay. Okay, my dear friend. Next, step number 3 is comparison between actual depth of neutral axis and limiting depth of neutral axis. Based on comparison, we can get at most 3 possibilities. Possibility number 1 is that your actual depth of neutral axis is less than limiting depth of neutral axis. Second possibility may be when both of these neutral axes are same. Okay, and third possibility could be when your actual depth of neutral axis is greater than limiting depth of neutral axis. Okay, so these 3 possibilities exist. Limiting depth of neutral axis is going to be a benchmark here because it is that value when strain at the time of collapse in concrete and steel is fixed. And what are these values? These are 0.0035 and 0.2% plus 0.87 Fy upon Es. Suppose if actual depth of neutral axis means actual depth of neutral axis, you can see it is based on the exact scenario. It is based on the, if I'll show you here, it is based on the grade of steel, grade of concrete. It is based on the area of steel with respect to effective cross section of rectangular beam. Okay, so actual depth of neutral axis depends upon so many factors. Whereas you have seen that limiting depth of neutral axis is only going to depend upon the steel only. Okay, it is independent of geometry. Doesn't matter whether you are talking about rectangular beam, triangular beam, circular beam, or any kind of beam. So limiting depth of neutral axis has to do nothing with the geometry. It only has to do with grade of steel only. Okay, but actual depth of neutral axis depending upon so many actual criterias like percentage of steel, cross section, geometry and all. Okay, so as I told you, there are total 3 possibilities. So possibility one, number 1 could be when XU is less than XU limb. Okay, if XU is less than XU limb, at that point of time you can see here strain at the time of collapse is fixed. But if XU is less than XU limb, so at the time of collapse, the strain at the level of CG of the tensile reinforcement will be greater than, it will be greater than this. So this scenario, in this scenario, we can read that steel is on the weaker zone. Here the steel is on the weaker zone. The amount of steel which is actually required is less than, which is actually provided here is less than actually required steel. So ideal condition would have been the amount of steel would have been slightly on the higher side so that the strain reaches here. But here the strain value on steel is higher. It means the quantity of steel in terms of area is less. So that is the reason why we call this section as under reinforced section. Means reinforcement is on the underside. We could have increased some amount of reinforcement. Okay, and you can see that based on actual depth of neutral axis, we are going to make the rectangular and parabolic block, actual stress block, and this value 0.36 FCKB into XU and its position is going to depend upon the actual depth of neutral axis, because you are going to calculate this value based on this parabolic plus rectangular stress block combination, and the depth of this combination is equal to the actual depth of neutral axis, isn't it? Next is, my dear friend, second case. Case number 2 is limiting case, when your actual and limiting depth of neutral axis are same. It means that actual scenario is matching with the limiting or balance scenario. Here the quantity of steel is such that whatever is the maximum strain has been developed at the time of collapse, okay, and whatever is the strain developed at the CG of the steel reinforcement at the time of collapse matches their permissible values, or that values which has been set by IES code. What are these values? At the time of collapse, the maximum strain in the concrete fiber should be 0.35%, and at the level of CG of reinforcement it should be 0.2% plus 0.87 FY upon ES. So it is matching here. This case is a standard case, and we also consider this case as a reference for the design of singly reinforced beam. So whenever we have to design a singly reinforced beam, so we are simply going to equate our external bending moment or factored bending moment with the limiting moment of resistance. Okay, so based on that you are going to calculate depth of the section, based on that you are going to calculate the area of steel. So design of singly reinforced beam is nothing but a special case of analysis when XU is equal to XU limb. But yes, in doubly reinforced section, design is somewhat conceptual and critical. Okay, so we will be watching that, don't worry. Okay, but singly reinforced beam design is nothing but MU limb case. So simply equate factor bending moment with MU limb, and we can get the value of D and all. Okay, I will tell you. So next case is case number 3, when XU is less than is greater than XU limb. This case is you can say is not supported by LSM, because under this case the assumption number 6 of LSM is not satisfied. What was the assumption number 6? So assumption number 6 was at the time of collapse, the strain at the level of CG of tensile reinforcement should not be less than. But if XU, my dear friend, is greater than XU limb, if it is greater than XU limb, then anyway this strain has to be less than this benchmark strain. Are you getting it or not? So this is the benchmark strain. But here this strain, this green strain is less than this particular value. So it is violating assumption number 6. So what we are going to do here? So we will be limiting our depth to XU limb only. That is the reason why it is called XU limb, because it is limited value. Our depth of neutral axis cannot exceed this XU limb. Okay, theoretically it is exceeding, but practically, my dear friend, we have to make this stress diagram for XU limb only, because collapse will happen here only when strain at the level of CG of tensile reinforcement and at the outermost compression concrete is equal to these set value. Okay, are you getting it or not? Tell me, my dear friends. So this is the way by which you can find the compressive forces. So what is important here, that in over-reinforced section, again for calculation point of view, you are going to take XU limb as your benchmark, as your actual depth of neutral axis, because although with respect to the area of steel XU is greater than XU limb, but it is not going to cross this value. So that is the reason why it is also called as limiting depth of neutral axis. Okay. In working stress method, although we have not covered it yet, so as I told you earlier, I am going to take a special session on that. But in working stress method, the similar depth is known as balanced depth of neutral axis or critical depth of neutral axis. But in limited state method, we are going to call it balance as well as limiting depth of neutral axis. Okay. Okay, we will talk about that later. Now, the final step is very easy. Why today we are watching the thing in a very speedy manner? Because I have already covered stress block study in the earlier class. We have seen how to get the value of net compressive force. We have seen how to calculate value of net tensile force. We have seen what is the position of this compressive force. What was it? 0.42 XU from topmost fiber. Then what about the remaining? If this is the scenario here, now what is this lever arm? Anybody? It is d minus 0.42 XU. It is d minus 0.42 XU. So moment of resistance is nothing but compressive force into lever arm, or you can say it is tensile force into lever arm. If it is compressive force into lever arm, then 0.36 FCKB into d minus 0.42 XU. If it is tensile force into lever arm, then the scenario is this. Okay. So this is the way to calculate moment of resistance. But yes, one thing which I want to conclude here, that as we have seen, there are total 3 possibilities with respect to position of the neutral axis: under, limiting and over. So if it is a case of under reinforced section, then you have to put here XU only. You have to put here XU only. There are total places for XU, this one and this one. So keep XU only. If it is a case of limiting section, at that point of time XU and XU limb are same. So again, no problem. Whatever you are going to put, either XU or XU limb, is same thing, because XU is equal to XU limb only. Actual is equal to limiting only. But my dear friend, in case number 3, what was case number 3? Case 3, when XU is greater than XU limb, it is over reinforced section. So while calculating moment of resistance, as you know, XU cannot exceed XU limb. So first thing is, you are going to replace XU with XU limb. Okay, although XU is different than XU limb, but still we are going to use XU limb, because I told you in earlier step we have to keep restricted this depth of neutral axis to axial limb only, because failure will occur this. So as per assumption number 6, strain cannot be less than this particular value at the time of collapse. Okay, so that is the reason why you need to substitute here axial as axial limb. Okay, and one more thing, even if you are substituting XU as axial limb, so you would be getting the correct answer from compressive side, but from tensile side you are not going to get the right result even after substituting here axial limb. You know why? Okay, so error is here. So this is right, lever arm is all right, because limiting and this is tensile force, so lever arm is all right. But 0.87 AST, and here in AST we are going to put the exact value of area of steel, and with respect to that value of area of steel, your actual depth of neutral axis would be lower. So numerically this is going to be equal to 0.36 FCK B into XU. But we have to find such a value of AST which is corresponding to 0.36 FCK B into XU limb. Okay, so that is the reason why even after substituting the value of XU as equal to XU limb, you are going to get the wrong result for moment of resistance. So I will recommend that either calculate that amount of AST which is corresponding to limiting condition, then replace your axial limb and you will get the right answer, or I will simply suggest you guys while calculating moment of resistance, simply go for compressive side formula. Okay, and compressive side formula is I think is better because when we will be watching doubly as well as the flange section, so again there would be relatively, you can say, lesser difficulty in calculating moment of resistance. Okay, because if you are even calculating the moment of resistance from tensile side, and when there will be more than one category of forces on compression side, then you have to calculate the CG of the resultant compressive forces, and in order to calculate the CG of the resultant compressive forces, so all the compressive forces will come into picture and their position will also matter. So why should not we calculate it directly from compressive side if we have to make all those arrangements? Okay, so I will recommend you to use compressive side formula in limit state method. Okay, okay, my dear friend. So I hope you get the point why it is not going to give you the correct value of moment of resistance in over reinforced section, because here XU is actually it is all right, but this AST is the actual amount of steel. If you want to use it, then first of all calculate that amount of steel which is a proportion to or which is equalizing 0.36 FCK B into XU limb. Okay, but that is a lengthy process. So why can't we use this simple compressive side formulation? Are you getting it or not? Okay, my dear friend. So this is the way to calculation to make a moment of resistance. Now, my dear friend, so after getting the value of moment of resistance, simply you can equate this moment of resistance with the maximum bending moment, may it be WL square by 8 in case of simply supported UDL, okay, or depending upon the beam condition, you can calculate it, and you will be getting the value of W, which is nothing but the factored bending moment. And if you want to calculate the exact, and if you want to calculate the, you can say, exact load, okay, yeah, safe load, or you can say working load, then you can divide the W value with the appropriate partial factor of safety, which is generally 1.5 for dead load and imposed load, isn't it? Okay, next, one more thing, this XU is XU in under reinforced section, this XU is equal to XU or XU limb in limiting condition, but this XU is XU limb only in over reinforced condition, that too on the compression side. So if you want to make a general thumb rule, then whatever is less among XU and XU limb, substitute that value. Whatever is less among XU and XU limb, simply substitute that value. You will never make a mistake then. Okay. Next, my dear friend, now we will be switching on to doubly reinforced section. In doubly reinforced section, the things are 80% same. Okay. One difference is going to come on the compressive side, because on compressive side earlier only concrete was effective, but in doubly reinforced section this time along with concrete, steel is also there. Okay. So many of you might be thinking, what is the necessity of steel on the compressive side? Okay. My dear friend, whenever we want to resist more amount of bending moment than a singly reinforced section, as we know that limit state method is not supporting over reinforced section. So had it been a case of WSM, in that case we could have easily increased the amount of steel and we could have gone for over reinforced section, and we would be able to resist more amount of bending moment with a limited size. But if size of the beam is limited and grade of the material is also fixed, okay, in that scenario what we can do, if we want to resist a higher amount of bending moment in a limited cross section and with a particular grade of steel and concrete, then my dear friend, we have to go for doubly reinforced section. Because anyway, by increasing the amount of steel on the tensile side, you may be increasing the tensile capacity of the beam. But you know that tensile capacity of the beam has to match with the compressive capacity of the beam, and compressive capacity of the beam is depending upon the XU value, and you know XU cannot exceed XU limit. So there is some upper limit of compressive force. There is some upper limit of compressive force. So with respect to steel, that upper limit if you can say is on the lower side, then what we can do, we can increase the amount of steel on the compressive side. So now the compressive forces of steel along with the compressive forces of concrete is going to challenge to tensile strength of steel. Okay. And one more thing is there, you can also think it like in this manner. If you are increasing the amount of steel on the tension side, then XU is coming down, XU is coming down, XU is coming down. A time will come when AST is corresponding to the limiting condition. At that point of time, XU is somewhere here and XU is equal to XU lim. If you are further increasing the amount of steel, then XU is again coming closer to the steel. Okay, but whatever depth it is coming down after XU lim, so that is making the section under over reinforced. So in order to pull back this CG neutral axis again on the to XU lim, what you need to do, you need to increase the density of the upper area, or you need to add more load on the upper side. Okay, so you have to compensate this difference by inserting some amount of bars on the compression zone, so that my neutral axis can again come back to its original position, again come back to its XU lim position. Okay, because till XU lim things are entirely effective. Okay dear. So in this manner we can think, in order to increase the moment capacity of a section with the particular grade of steel and concrete and with the fixed size of cross section, we can adopt our doubly reinforced beam. So when steel is also going to come in compression side, now what is going to happen, my dear friend? The changes will come in step number 2 and in step number 4, because step number 1 was XU lim, that is quite obvious. Step number 2 is calculation of actual depth of neutral axis, and in actual depth of neutral axis now we have to calculate the exact compressive forces. Okay, step number 3 is again comparison, and in step number 4 as well. Earlier we were equating 0.87 Fy AST with 0.36 FCKB into XU, but along with the 0.36 B FCK XU, one more component of force will come, and that would be obviously due to the presence of steel, isn't it? Okay, so let's proceed with this 4 step. So step number 1, no need to repeat, no need to repetition, because XU lim is same only. XU lim is 700 upon 1100 plus 0.87 Fy into D, and again depending upon the grade of steel, generally these 3 grades are used in majority: 250, 415 and 500. So you can see here that it is 0.53 D, 0.48 D and 0.46 D for 250, 415 and 500. Okay. Now step number 2 is quite interesting. If you are getting step number 2, then entire picture of analysis of doubly reinforced beam is also clear to you, my dear friend. Okay, so let's see that. Axio. My dear friend, in earlier lecture I also told you that steel is not going to disturb you because it is expensive. Whatever, this time as well steel is not going to disturb you. This is 0.87 Fy, quite simple, 0.87 Fy upon 1.15 partial factor of safety into As, that's all. Okay, no need to take tension of this, just forget it. Now, it is a steel on the compressive side. It is the steel on the compressive side. Okay, so now as well steel is not going to disturb you, but steel is occupying some space at the cost of concrete. So there is some amount of concrete which is absent here due to the presence of steel. So we need to make now corresponding calculations and corrections. Okay, so now we'll see. I am simply focusing on the compressive side. I am simply focusing on the compressive side because tensile side is still 0.87 Fy into AST. Okay, so I am focusing on the compressive side. So just see here, this is concrete block. Okay, this is concrete block, and there are two bars. Let me call it ASC. First of all, I am considering only compressive zone. Okay. Now, if I want to reach till here, and this is entire concrete, then I have to subtract some amount of concrete which was not available there. Why that was not available? Because at that location steel was available. So the entire rectangular block B into XU minus this concrete equal to area of steel in compression plus area of steel in compression is going to give you the exact this original scenario. Okay, so total, my dear friend, there are three components of the compressive forces. Component number 1 is due to this concrete block and it is 0.36 FCK B into XU. Now, what is not present? What is not present? This amount of concrete is not present. What is that amount of concrete? That amount of concrete is equal to the amount of steel. Okay. So, at this level, my dear friend, at this level, there is one assumption always that whatever is the depth of top cover, this top cover is always going to fall in the rectangular stress block, rectangular portion of the stress block. Or in other words, we can say that this is assumption in IS code that top cover depth is always less than equal to 3 by 7 of XU, because 3 by 7 of XU is the depth of the rectangular stress block. Okay. So if such is the case, then the amount of stress developed at the location of concrete which was not present, that is equal to 0.45 FCK. Because, my dear friend, your stress diagram is like this only. Your stress diagram is like this. You know, it is like this. So you can see that it is also lying up to this scenario. This is 0.45 FCK. Okay. So what is area? Area is area of steel. It is area of concrete only, but numerically this area of concrete is equal to the area of steel in compression. Now plus. Now come to the concrete, steel. Let's suppose the amount of stress developed at this steel is FSC, stress in steel in compression, and multiplied by here. So the resultant compressive force, which is there due to concrete, which is there due to non-availability of concrete, and which is there due to the presence of steel, is given by this combination. And net compressive force is equal to 0.36 FCK B into XU plus FSC minus 0.45 FCK into ASC. That's all. So this is the net compressive force. This is the net compressive force. Are you getting it or not? This is the net compressive force. And again you can see steel is not disturbing you even on the compressive side. It is again concrete, due to which you are getting complications. Complication is due to this thing. Complication is due to the non-availability of concrete. But when it comes to the stress of steel here, or you can say compressive force of steel, it is quite simple. It is FSC into ASC. But let me tell you one thing, in most of the design problems, for simplicity, what they normally adopt, this is net compressive force due to concrete, this is net compressive force due to steel. So they simply going to add both of this. Okay. From design point of view, it is also not wrong, because it is very minor component. If you are going to compare this component with respect to FSC into ASC, then this value is quite less. Are you getting it or not? Because 0.45 FCK for M25 or M30 is in the order of 10, 11, 12 like that, and FSC is in the range of 350, 340 like that. So the amount is quite less. Okay, but my dear friend, for our exam, for GATE exam, we will be giving importance to this component as well. Otherwise, it may lead to the negative marking, because they want us to be 100% conceptually right. Okay, logically, if you are even ignoring this portion, that is also not wrong. But at our level, at our analysis portion, we need to give the importance to 0.45 FCK into ASC. Okay, okay, my dear friend. So compressive force is this only, tensile force is this only. So there are total two component of compressive forces. One is 0.36 FCK BXU, which is due to the presence of concrete, and it is acting at a distance of 0.45 0.42 XU from the topmost fiber. And the second component, which is due to the non-availability of concrete and due to the availability of steel in that area, that is going to pass at a distance of DC from topmost fiber. Okay, so if we are going to see that, in that case, my dear friend, so 0.36 FCK BXU is located at a distance of D minus 0.42 XU, and this is located at a distance of DC, and lever arm for this is again quite simple. It is D minus DC. Okay, D minus DC or D minus DC dash. Okay, so this is the calculation of XU. This plus this is equal to this. Okay, next is comparison. My dear friend. So in comparison, we know that there are total three cases. Case number 1 is under reinforced section, same. Case number 2 is you can say limiting section, and case number 3 is your over reinforced section. So scenario are exactly same. So all again these three possibility, but yes, in possibility number 3 again we are going to restrict our actual depth of neutral axis to XU limb, because we cannot exceed XU limb. If we are exceeding XU limb, then strain at the time of collapse at the level of CG of tensile reinforcement is less than 0.2 plus 0.87 Fy upon ES, which is not allowed as per assumption number 6 of a limit state method. Are you getting it or not? Okay. Now the final step. I will explain you why I was telling you avoid tensile side formula. So now see, moment of resistance is again very easy. So 0.36 FCK BXU compressive forces due to concrete into lever arm plus FSC into ASC is due to steel, and minus 0.45 FCK into ASC is due to non-availability of concrete. So it is the net compressive forces due to the steel combination, and for that the lever arm is D minus DC. So it's quite easy. Compressive force 1 into lever arm 1 plus compressive forces 2 into lever arm 2. Okay. So 0.36 FCK BXU into D minus 0.42 XU plus FSC minus 0.45 FCK into ASC into D minus DC. And if you want to calculate the moment of resistance from the tensile side, then it is 0.87 Fy into AST, but D minus Y bar. What is Y bar? My dear friend, Y bar is the net compressive force For example, if net compressive force is lying somewhere here, so for that you need to calculate this y bar here. And in order to calculate the value of y bar, you need to know 0.36 FCK BXU into 0.42 XU plus this quantity into DC dash divided by this plus that. Then you are going to get the y bar. If you have to do that much amount of work in order to calculate the value of y bar, then why can't you calculate the moment of resistance from compressive side only? You are doing that much of work. Even after that, there is restriction. There is restriction. What is that restriction? That in over-reinforced section, you cannot proceed with tensile side formula. You cannot proceed with tensile side formula because again, you need to correct the value of AST. You have to take AST corresponding to limiting condition. Then you are going to calculate y bar. So it's always advisable in LSM, especially in doubly reinforced section and in plain section, that go for compressive side moment of resistance formulation. Okay, it is quite simple. If it is a case of under reinforced section, then XU is equal to XU only. If it is a case of over reinforced section, then XU is equal to XU lim only. If it is a case of limiting condition, in that case XU is again equal to XU lim only. Okay. So whatever is less among XU and XU lim, simply you are going to place that in this scenario and you will be getting the exact moment of resistance. Are you getting it or not? So this is the case, my dear friend. After that, my dear friend, we will be seeing the third aspect of today's session, which is design of doubly reinforced beam. Okay, so we will be watching the design of doubly reinforced beam now. Okay, so in design, first of all, we are going to see that how to develop a design formula. Okay, so here the total compressive zone, as I told you earlier, is divided into two parts. Not in fact two parts, even three parts. One, entire concrete. Second, absence of concrete at the location of compressive reinforcement. Third, presence of steel. Okay, so what we are going to do? First of all, we are going to calculate. MU lim, and this MU lim is simply, it is QBD square, or it is 0.36 FCK B XU lim into D minus 0.42 XU lim. Okay, means moment of resistance corresponding to the limiting condition. My dear friend, let's suppose if we have to resist FBM, and if FBM is greater than MU lim, then only we will be needing the doubly component. But if FBM is less than MU lim, then no need to go for doubly reinforced section. We can tackle the section in singly reinforced mode only. Okay, so if factored bending moment is greater than the limiting moment of resistance for this particular size and grade of concrete steel, then only we will be needing W1. So first of all, we are going to calculate MU lim, and we will be designing here the area of steel. Let me call it area of steel zone number 1, means 1 for MU lim, and for remaining bending moment. What is the remaining bending moment? Let's suppose it is MU2, and how you can calculate MU2? It is the total factored bending moment minus MU lim. It is the total factored bending moment minus MU lim. For MU lim, we are going to calculate AST2, area of steel in tension, for the axis bending moment, and area of steel in compression for the axis bending moment. Means if let's suppose the factored bending moment is 200 and MU lim value is 150, then for 150 we are going to design area of steel AST1, and for remaining 50 we are going to balance it with area of steel in compression and area of steel in tension. Okay, So for area of steel in tension, we are going to equate it with the 0.87 Fy into JD. For area of steel in tension corresponding to axis bending moment, we are going to equate it 0.87 Fy into D minus D dash. Okay, that is the net force per unit area. And ASC, for ASC we need to know the strain at this level, because if we are knowing the value of strain at this level, we can calculate the value of stress from the design stress strain curve, and after the value of FSC you can get the value of ASC by equating axis bending moment with 0. Or you can say FSC minus 0.45 FCK into ASC into D minus D dash. Okay, okay my dear. So mu lim is nothing but mu1, for which you are going to design your AST1, and the mu2 is the axis bending moment, for which you are going to design your ASC and AST. Okay, are you getting it? Okay, so this is quite simple. So mu lim here, mu lim is 0.87 Fy, AST1 into D minus 0.42 XU lim. It is also called as JD. Okay, so what is AST1? What is AST1? So AST1 is mu lim divided by 0.87 Fy. Let me call it JD. Let me call it JD. Okay, and AST2 here. AST2 here is similarly, we can design it for the axis bending moment, and axis bending moment, as I told you, it is mu2, and mu2 divided by what is there, 0.87 Fy into D minus DC into D minus DC. So this is the value of AST2. And my dear friend, for getting the value of ASC, you need to know the value of FSC, and for FSC, first of all we need to know what is the strain at the level of this position, at the CG of this tensile reinforcement. Okay, from there we are going to refer the stress strain curve of steel, and from there we are getting the value of FSC. Once the value of FSC is known to you, then you can get the value of ASC again by equating mu2 equal to FSC minus 0.45 FCK into ASC into D minus DC. So ASC would be mu2 divided by FSC minus 0.45 FCK into D minus. So this is the way. Okay. So like that we can get the value of steel. So now the resultant area of steel in tension is the summation of AST1 and AST2, and the resultant area of steel in compression is ASC. So in design problem we only have to compute these three categories of area of steel. So first category is tension 1 and 2, and another category is area of steel in compression. Okay. So my dear friend, this is all about the design formula. So if I want to conclude it in step manner, then you can see, first of all, what all are the values which are given to us. So values given are section, or you can say BD, grade of concrete and steel, bending moment or factor bending moment. And what we have to find? We have to find the area of steel in tension as well as the area of steel in compression. The total 3 times area of steel we have to calculate, 2 times for tension zone, one for mu1 and another one for mu2, axis bending moment, and third time we are going to calculate ASC. Again corresponding to mu2, means for axis bending moment. Means if I want to split my total system into 2 parts, then this part number 1 is responsible for AST1. Okay, so you can say in first zone this resultant concrete is going to tackle the problem with its corresponding steel. AST1 is that area of steel which is corresponding to 0.36 FCKB into axial limb, and the axis amount of force which is available due to FSC minus 0.45 FCK into ASC is going to tackled by 0.87 Fy into AST2. Okay, so this is for AST1 and this is for AST2 and ASC. So rest of the things we will be watching in the design, my dear friend. So here you can see that these are the steps. So what we have to find? We have to find the area of state. So first of all, we are going to calculate mu lim, or you can say mu1. Then if FBM is less than mu1, as I told you earlier, no need of doubly. But if FBM is greater than mu1, then we need a doubly reinforced section. First of all, we are going to calculate axial lim. We are going to calculate ESC. Then we are getting the value of AST1, then AST2 and ASC. Are you getting it or not? Tell me, my dear friends. Okay, so now we are moving on the numerical phase. So total 3 numerical we will be covering here. So without wasting time, so here is the numerical 1. Calculate the moment of resistance of a singly reinforced beam shown in the figure. We can use M25 concrete and Fe415 steel. Okay. So analysis of singly reinforced section is totally divided into 4 parts. Calculation of axial lim. Second, calculation of XU. Third, comparison between XU and axial lim. And fourth is calculation of moment of resistance. So my dear friend, let me start with the first step. So first step is limiting. Limiting is what? XU lim only. It is nothing but 0.48 times of D. Why 0.48 I am considering? Because here the grade is 415. The original formulation of axial lim is equal to 700 upon 1100 plus 0.87 Fy multiplied by D. If you are going to substitute the value of Fy as 415, you are going to get 0.48. Okay, so axial lim is equal to 0.48 D. Okay, in step number 2, we have to calculate the value of XU. So how we can get the value of XU? By equating tensile force and compressive forces. So it is like this. Okay, so 0.36, FCK is 25, and what about B dear? B is 400 and XU we need to calculate. This is equal to 0.87 into Fy into AST. AST is 3 bars of 16 mm dia. 3 bars of 16 mm dia. So if you are going to solve it XU, so XU you will be getting here as how much? It is 60.5. You are going to get a 60.5, isn't it? Okay. So 16.5 mm. So and axial lim is basically, axial lim is 0.48 D and it is coming out to be 300 mm. It is coming out to be 300 mm. Okay, let me check once. Is it 300 mm only? Or it's something else? Okay, it is not 300, it is 360. It is 360, yes. It is 360. So section is, if you are going to compare these value, then section is under reinforced section because XU is less than XU lim. Okay. So now if we are going to calculate the moment of resistance, so moment of resistance in singly reinforced beam under reinforced section is given by 0.36 FCK B into XU into, we are going to use XU only, D minus 0.42 of XU. Okay. So you will be getting the answer in Newton mm. What about B? B is 400 mm. XU is 60.5 and D is 3, not 3, it is 750 minus 0.42 of 60.5. You will be getting answer in Newton mm, and on solving this equation what you will be getting. So in the kilonewton meter, I am giving you the answer. So this would come in Newton mm. So on kilonewton meter, you will be getting 157 point, or it is 157.8, around 8. Okay. Okay. So convert that Newton mm into kilonewton meter. Convert that Newton mm into kilonewton meter. Okay. Now the next question. Dear. Determine the ultimate moment capacity of a doubly reinforced beam whose B is equal to 300 mm, D is equal to 600 mm, area of steel is 2060, and area of steel in compression is 804 mm square. Effective cover we can take 50 mm on both sides, and we have to use M20 concrete and Fe415 steel. Okay. FSC is given to us. My dear friend, FSC is 0.968, and what about FYD? FYD is nothing but design yield, so 0.87 of FY, and FY is 415. So don't think FSC is not given to you, FSC is given to you. Okay, so let's solve it. So again a analysis problem, dear. So this is again divided into 4 parts. First part is calculation of axial limb. So we all know how to calculate the value of axial limb. Again the grade is 415, and for 415 grade axial limb is 0.48 into D, and 0.48 into D is here how much, dear? Effective cover we are going to take of 50 mm. So effective depth is 550. So it is 8 times of 550. So I think it is coming out to be it is 264. It is 264 mm. Now step number 2 is XU. For getting the value of XU, what we need to do? We need to simply equate our compressive forces with the tensile forces. And for compressive forces, here total how many components are responsible? For compressive forces, here my dear friend, 2 components are responsible. Okay. So first is how much? 0.36 FCK B into XU, plus second component is FSC minus 0.45 FCK into ASC. This is going to equate with the net tensile forces, which is 0.87 Fy into AST. So my dear friend, in this particular question, the AST, ASC, FSC, everything is given to you. So if we are going to substitute the value of FCK as 20, B as 300, XU you need to find, FSC is also given to you there, and 0.45 FCK, and ASC is again given to you, FI is given to you, AST is given to you. So on substituting the value here, so XU is equal to, XU is going to come equal to 217.6. I have already calculated, I have the answers with me. So okay, so what is the ideal approach? Ideal approach is, whenever I am discussing any question, so after reading the question, after getting the question, pause the video, okay, and try to attempt that question by your own. Okay, so after that you need to simply match your results with my result. So I have already calculated these values, so I am directly writing here. Okay, so calculation you can check it out, and chances are there that error can happen even by me as well. If you find any error, if it exists, then please mention it in the comment box, so I can edit it and make it proper. Okay. Okay, dear. Now the third step is comparison. So here again you can see the value of XU is less than XU limb. So section is an under reinforced section. So here XU is less than XU limb. So section is again under reinforced section. Okay. So in under reinforced section, how we are going to calculate? Dear? In under reinforced section, how we are going to calculate moment of resistance? So moment of resistance is equal to 0.36, means compressive forces into lever arm, that's all, FCK B into XU into D minus 0.42 XU, okay, plus another component is FSC minus 0.45 FCK and ASC into D minus D dash, okay. So substituting the value here, you know the value of FCK, FCK is 20, B is 300 and XU we have calculated 217.4, D is how much? D is 550 and FSC is given to us 0.968 into 0.87 into Fy. FCK is also known to us, ASC is given to us, D minus D dash is I think 500, 600 minus 50 is 500 because the effective power is 50 mm on both the sides. So this you will get the answer in Newton mm. So I am converting the answer into kilonewton meter. So the final answer is 352 point, how much it is in kilonewton meter? It is 28. Okay. Your answer may vary even in decimals, so no need to take much tension for that. Are you getting it or not? Okay. Now the final questions. Final question is a design problem. So the size of the beam is restricted to 250 cross 500 mm. It is overall. It is going to carry a superimposed load of 25 over a span of 6 meter, including self weight. Means we need to calculate self weight as well. We have to determine the reinforcement by LSM if M20 and Fe415 are used. And effective cover we are going to use at 50 mm. Okay. So let's start here. So the very first step is to calculate the factored bending moment. Okay. We have to calculate what? We have to calculate the factored bending moment. But for getting the value of factored bending moment, my dear friend, you need to calculate load. So step number 1, I am calculation of factored bending moment. So for that we need to calculate load. Load is, superimposed load is how much? It is 25 kilonewton per meter, and dead load is how much? It is 25 is the density. And what is the cross section here? Cross section is 250 cross 500, 250 cross 500. So this you will be getting 3.125 kilonewton per meter. So the total load W is superimposed load plus dead load or self weight of the beam. It is better to say self weight. Total load is going to be 28 point, total unfactored load is going to be 28.125 kilonewton per meter, and total factored load W is 1.5 times of W. So it is going to be how much? So this value is going to be equal to 42.188 kilonewton per meter. So now if you are going to calculate the factored bending moment, so factored bending moment for simply supported condition is WU L square by 8, and what about span? WU is 42.188 and span is how much? It is 6 meter. So 6 square by 8. So in kilonewton meter, you will be getting 189.84. You will be getting 189.84. Okay. So this is the factored bending moment. Now step number 2, we are going to calculate in step number 2 MU limb, because the comparison has to be made between MU and MU limb, factored bending moment and MU limb. So MU limb is how much? MU limb is how much, dear? MU limb is 0.36 FCK B XU limb into D minus 0.42 XU limb. XU limb you can substitute here 0.48 D. So in kilonewton meter, if you are calculating the value of you can say MU limb, so it is coming out to be 139.68. D I am taking how much? D I am taking 500 minus 50, 450. So it is 139 point, how much? It is 139.68. It is 139.68 kilonewton meter. So obviously we have to go a design with doubly reinforced beam, because the factor bending moment, you can see it is greater than mu limb. So for 139.6 we are going to calculate AST1, and for axis bending moment, what is this? You can keep equal to mu1, and what is mu2? mu2 is how much? It is 189.84 minus 139.68. I think some 50 will come, 50.15 kilonewton meter. Okay. Now calculate AST1, AST2 and ASC one by one. But yes, for ASC we need to calculate the value of strain. Okay, and for that strain you need to interpolate the values. So for calculating strain, what we can do, we know that 0.0035 is the strain at a distance of 0.48 times of D, and strain at the level of compression reinforcement is equal to 0.48 times of 450 minus 50. So here the strain value is coming out to be 0.00268. Okay, please double check the calculations by your own as well. And for this 0.00268, what FSC value is coming? The FSC value is coming out to be, it is going to lie between here. And the FSC value here is going to be 349.5. It is on linear interpolating, it is 349.5. I hope you all know linear interpolation. 343 plus numerator 352 minus 343, denominator this minus this, multiplied by that strain value minus 0.00241. So by linear interpolation you are going to get the value of 349.5. So this 349.5 value you will be using there, dear, and so AST1 is how much? It is mu1 or mu limb upon 0.87 Fy into D minus 0.42 times of XU limb. Okay. So if you are getting putting the value of mu1 139 into 10 raised to the power 6, 0.87 FYD and XU limb. So you are going to get area of steel as 1076.8 mm square. Similarly, if you are going to calculate the value of AST2, AST1 is for mu1 or mu limb and AST2 is for mu2. It is again 0.87 Fy, but the lever arm will be different. It is D minus D dash. So if you are going to calculate the value of AST2, so this value is coming out to be 347.25 mm square. So you can say that the net tensile reinforcement AST is equal to AST1 plus AST2. So it is equal to how much? 0.5. Okay, so it is 1424.5 mm square. It is 1424.5 mm square. When it comes to ASC, so ASC is simply mu2 divided by point, or you can say FSC, which we have already calculated, minus 0.45 FCK into D minus D dash. So on substituting the value of FSC, D minus D dash and all, you will be getting ASC as 368.2. So my dear friend, this is the net compressive reinforcement, this is the net tensile reinforcement, and in question we are asked to do the same. Are you getting it or not? Okay. So we need to determine the reinforcement by LSM. So net tensile reinforcement is 24.5 mm square, and net reinforcement in compression is 368.2 mm square. Okay. So my dear friend, these three questions explain the theory which I explained in the earlier portion of this video. Okay. So next session we will be watching on day after tomorrow, and we will be covering flange section. Okay. So thank you, thanks a lot. Okay. And okay, yes, this one is assignment for you. This one is assignment for you. Okay, my favorite question, you can say, probability question. Intentionally I am not going to solve it now. One time it has been asked in GATE and several times in ESC prelims. Okay, so try to attempt this question. So we will be discussing it in next class based on your comment and all. Okay, so that's all on today's session, dear. So thank you, thanks a lot. Bye bye.